So when it says you are neutralizing substances, you're adding an acid to a base, right? They does actually give off a certain amount of heat, right? It actually feel the container giving off heat, right? So heat of neutralization could be found. Heat of neutralization is the energy change that occurs when 1 mole of water is formed or liberated during the neutralization of an acid and a base, right? So you're using the same formula, E is equal to mc delta T, right? This is what I want to let you take down here, this bit of information, and we're going into the example. 2 minutes and we're going into the example. Right, are you ready? So let me go. Example, 50 cm cube of 1 mole per dm cube of sodium hydroxide at room temperature was placed in a plastic cup. 25 cm cubes of 2 moles of mole per dm cube hydrochloric acid is placed at the same temperature and added to the alkali. The temperature row is at 9.1 degrees Celsius. They want you to calculate the heat of neutralization. My advice to you when you're doing these particular types of questions, please write down everything that they give you in the question. They give me the concentration of the sodium hydroxide, I write it down. They give me the concentration of hydrochloric acid, I wrote it down. The reason for that is to make calculation easy, right? They give me the volume of the hydrochloric acid, I write it down. Volume used of the sodium hydroxide, I write it down. But the temperature changed by 9.1. And always remember the specific heat capacity is 4.18. Some papers will give it as 4.2 to make your calculations easy. Take down this part because I want you to use this information to go with the calculation next, right? So you'll have it in front of you. 2 minutes. All right, moving on. So everybody have this part. Right, so I have this stuff broken down step by step as to what you need to do. First and foremost, we need to calculate the moles of the alkali used. So the number of moles in the volume, this is the equation you're using. So you would have learned this when we're dealing with moles. Volume given, divided by 1,000 or 1 dm cube, multiplied by the concentration in moles per dm cube. Volume given in the question was 50. It's given in cm cubes. So we're using 1,000 here. And the concentration of the alkali given is 1. So you end up with 0.05 moles. Guys, are you all with me so far? Let me know. I ain't seen no thumbs up here, so I don't know for sure. All right, so Akila saying yeah. Janine, yeah. All right. Kyle, Yashana. All right. Now you're doing the same thing for the acid. You're calculating the number of moles of the acid used. So its number of moles in a volume is equal to the volume given divided by 1,000 or 1 multiplied by the concentration. So the volume given in this question is 25. We're using 1,000 because it's given in cm cube and the concentration is 2. So you get 0.05 moles. So yes, when neutralization reaction is occurring, you need equal moles of the acid added on to equal moles of your base in order to get cancellation, neutralization. Step 3, write a balanced chemical equation for the reaction. Sodium hydroxide added on to hydrochloric acid gives you sodium chloride and water. So by this equation here, when we were looking at quantitative relationships, when we're dealing with moles, we will know theoretically, you're supposed to use 1 mole of base added on to 1 mole of acid, according to this question, to get 1 mole of your sodium chloride and 1 mole of water. I ain't seeing no 2 and no 3 and no 4 in front of none of these things. So everything here is at a 1-to-1 ratio. So because it's at a 1-to-1 ratio, right? For one of the moles for the base divided by the number that occurring frequently, which is 1, multiplied by 0.05. So across the board, once I multiply by 1, it will be, you didn't use a mole, you use 0.05. So you're supposed to use 0.05 moles of the base added on to 0.05 moles of the acid to get 0.05 moles of sodium chloride and 0.05 moles of water. Right? Find the total mass of the solution. So you add in your solute and your solvent, which is 50 added on to 25, you get 75 cm cube. Find the heat of neutralization for 0.05 moles. So it'll be MC delta T, the mass is 75, your specific heat capacity of water is 4.18, and the temperature rose by 9.1, so it is 2,852.85 joules. For 1 mole, it will be that same value you calculated by divided by the 0.05 moles. So it's 57,057 joules because of the fact that with neutralization reactions, they give off heat. You just put a minus in front of it to indicate that it's an exothermic reaction. And that's basically it. It's actually even shorter for exams too because it doesn't even have to find a mole ratio. So I want you to take this bit of information down for me. And when you're finished, I'm going to give you 1 and then we're moving on. Right, so when we're talking about rate of reaction, we're talking about a change, a measurable change, something you could see or you could weigh during a specific amount of time. So it's a measured change in a property over a period of time. right? Now, when reactions occurring, the reactant's supposed to decrease and the concentration of the product supposed to increase, right? And you can tell a reaction is occurring based on the, if it doesn't have gases produced, the volume of the gas produced, how intense the color is. Did it get, did the color get darker or did it get lighter? It's a precipitate form. How much is formed? And the reduction of mass of your reactants, right? Now, in order for collisions to occur, reactions to occur, particles must collide, right? They had to bounce into each other. The particles of the reactants have to bounce into each other in order to bring about the bonds breaking and the bonds forming. So you have to have collision occurring. So the particles must collide, but they must also collide with enough energy to cause the bonds to break and to cause new bonds to form, right? Now, there are some factors that affect, well, 6 in total, that affect the rate of the rate of reaction. So the first one is concentration. And if the concentration increases, it's believed that the rate of reaction will increase because of the fact that when you increase concentration, you have more particles. Increased concentration equals increased particles. When you have more particles in a confined space, they're going to bump into each other a little bit more. And because of the fact that that frequency of them bumping into each other increases, you have your reaction increases. And there is a experiment that I want to show you. I don't know if only do this in school, but I want to show it, right? And this is what you call the disappearing cross experiment, right? And with the disappearing cross experiment, they are basically manipulating the concentration of something called sodium thiosulfate. And we're going to see which one going to react the fastest. Hold on a moment. So let's talk about pressure, right? Now, pressure only applies to gases alone. It don't affect any other particles, solids, or liquids. Only gases, and that had to do with their random motion, right? Now, if you increase the pressure of a gas, the rate of reaction increase. And by increasing the pressure, say come like, well, you know, all of them can sprays, or they have them aerosol sprays, perfume, or in the aerosol sprays, or fly sprays, or whatever. Let me see what how. These kind of spray bottles, right? These things. When you shake them and you spray it kind of becomes pressurized, right? And one of the things they tell you is don't store this in heat and don't try to compress the can. Reason for all that is because when you increase the pressure, the volume, the space that these particles had to move around in decrease. When that happens, your particles going to collide more frequently. And when they collide more frequently, your reactions occurring faster. Temperature. When temperature increases, the rate of reaction will also increase. Temperature gives your reaction energy. And when you give your reaction more energy, guess what? Your rate of reaction is going to speed up, right? So giving you one with temperature now. Let me talk about particle size, right? So they say by decreasing particle size, it will decrease the rate of your reaction. So I'm just giving you two scenarios here, right? So a drawing, so everybody know what these sugar cubes look like, right? It's literally be a cube of sugar. So this drawing here is just to represent a sugar cube. right? That's my sugar cube. And then we had the little grains of sugar that we just put in with tea that we just buy in the grocery. So two of them we could put in tea, right? In your opinion, you can tell me on the chat if you want. In your opinion, if you take a sugar cube and you put it in hot water and you put the sugar grains in hot water, which one you think going on dissolve faster in the hot water? Anybody? Which one do you think going on dissolve faster? Hello? We have 2 cups of hot water. We put the sugar cube and we put the greens. Which one going to dissolve faster? The cube or the green? Definitely the greens. And the reason for that is because heat have to penetrate every single layer of this cube before it reaches to the bottom. Whereas the grain particles so small that heat going through and through that cube in no time, so it would be able to dissolve it. So that's an example of regarding particle size. When you're boiling potato, I don't know how many of you all here is in the kitchen, but if you put a whole potato to boil, 2 hours gonna meet you and that center of potato is still hard. The outside might be soft, but the inside might be hard. And your mother tell you have a half an hour to make potato salad. So, the better thing to do is to cut the potato into smaller pieces so the heat can penetrate it faster. Because the reaction takes place on the surface of your substance. And if it is the reaction, it had to penetrate all of those layers, it would take too long. So when you break up your particle size, it's definitely going to cause the reaction to occur faster. And now I'm going to show you an example of it, right? I could actually do this one here home. Give me 2 minutes. Hold on. Trying to see how I could set up so that you all could see. Hold on. 1 second. Right. So I have 2 sets of that's not one. Right. So I have 2 sets of water here, right? I try to get them in equal glasses as possible. And what I'm going to show you here now, so I have vitamin C, right? I have this one here in the packet. So it's redoxon I'm using right across the board. But in the first redoxon, I leave it in whole, right? So me, I'm mashing up this one. So this is my whole vitamin C capsule, right? And then, oh, hope I have everything here. So I just pounded this one out to decrease the particle size, right? So I'm not sure. Right. So guys, so this is the same vitamin C capsule, but it's in powdered form, right? Now, we just established that in rates of reaction, if you decrease the particle size, the reactions may occur faster, right? So let me see which one of these solutions here going to dissolve faster. So I'm just going to put in my particle, the powdered one first. Get all of that in there. Right? And I put this one here. And if I look at the noticeable difference in the colors of the water. This one's still looking a bit diluted. This one here, the particles on them already almost done dissolving. All right? So give it a few minutes. Even though this one put in after, what's something? It's still fizzing. So this one dissolve out, right? This one dissolve out. There had nothing to dissolve in this one. That one done dissolve out. Check out this one here. From the top, you could still see, hold on. Trying to record it as well from another view. So like I have it. Right. So in this particular one, from the top view, you can still see that it dissolving. Right? So that just goes to show you that particle size does make a difference with rates of reaction. Decrease the particle size, faster the rate of the reaction. All right? Catalysts now. Catalysts, once they are added to a reaction, they're going to speed up the rate of reaction, causing the reaction to go faster. And that's because it lowers the activation energy. So therefore, it will increase the rate of reaction. Right? Any questions so far, guys? Any at all? All right. Light could work for some reactions, like for instance, photosynthesis. Light actually increases the rate of reaction. So the more light plants are given, the faster that they photosynthesize. When you are plotting curves, these are the curves that you plot. Products, their concentration will increase. Reactants, their concentration will decrease. So this is just basically the typical shape that you would take, right? This is another graph that you may have to plot, which is the amount of concentration of products, right? And obviously you're gonna have like, if the reaction, I have a catalyst, and then you have like, if it is, you manipulate a factor to increase the rate of a reaction, right? Yes, you do have to know an energy profile diagram for these particular reactions. So this is the typical one that you have to learn. The reactants will be here without a catalyst. Yeah, this is what it will happen with regards to the graph. When you add a catalyst, the reaction, the activation energy is lowered, so the reaction pathway is faster, right? So this is the original rate curve for amount of product. B is if it is the increase of concentration, increase the pressure, increase the temperature, add a catalyst, you see the reaction happen faster, right? That's if you manipulate one of the factors. So the curves are really basically given as a guide as to what could take place, all right? Wherever you have your slope in your graph, that is where you have the greatest amount of your reaction taking place. And that's it for rates of reaction. So those particular notes I will post for you on the Google Classroom. That is it for today, guys. In the next session, I am going to start organic chemistry from now. Metals and non-metals could do after, but I really want to do organic chemistry. From next week, we are reverting back into our regular schedule. So we have plenty work to push. And how to start a schedule out probably this weekend. I'll let you all know what Sunday I will be taking all you to do a crash course. So it would be like 2 hours in the morning, you get an hour break, and then 2 hours in the evening, right? So it'd be like a 9 to 2 now. So I just had to try and see to move around a couple of things. But I'm taking only for a whole Sunday. And I have some solutions to send for you as well. So look out for a drive file by tomorrow or Saturday. So guys, that is it for today. You all could go ahead and leave. Bye, everybody. Bye-bye.